Welcome to Jeremy's IT Lab. This is a free, complete course for the CCNA. If you like these videos, please subscribe to follow along with.
Minimum value of data length 20 bytes. And finally was more frame set to 0. Source IP address is IP address 4 bytes 32 bits. The identification field is 16 bits. View the startup configuration. Show startup config. Estimator FCS is 4 bytes. Which field is the operator relationship DSCP. When router receives packets, they look in the routing table. The next router one is called next hop. The IHL field specifies the length of the header in 4-byte increment. Code blah 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 in the routing static root S. If a packet's destination IP is matched by multiple, which route is will the router select with the most specific routing or match with more prefix. And the flex field is 3 bits. Checksum field is 16 bits. A default route is a route to 0.0.0.0/0. What is the minimum length of IP4 header? 20 bytes. Local route use a prefix length of local 32. What does L local? IPv4 header version field is 4 bits. What is the maximum value of total length? Total length will be 60 bytes. Okay, again. Value of protocol, value of 89. 17 UDP. Value of the version indicates version. Value of 60110. Display the configuration of its interface on a router. Show interface description. Value of 6 TCP. TTL field is yes, it's 8 bits. What will a router do if none of its route match a packet? Drop the packet. Protocol field is for 4 bits, 8 bits. Route is to the actual IP address configured on the interface. Actual IP address. Static, local. IPv4 protocol field UDP is 17. Maximum value of IHL field 15. Internet header length. Total length of the packet. Total length field is 16 bits. ECN is 2 bits. Maximum transmission unit. Bit MF is more frame, so bit 2. Which is to check for errors in the header. Checksum. Configure a static route specifying the exit interface. IP route, IP address, net mask, exit interface. All fragments of the same packet will have the same value in the identification field. Route is connected. What does ECN? Explicit congestion notification. Code in route candidate default route asterisk. IPv4 header protocol field value of TCP is 6. IPv4 header flags field. What does the F stand for? Don't fragment bit. A blah blah route is added to the routing table by a protocol dynamic. Configure a static route specifying the exit interface and next hop IP. IP route, IP address, net mask, exit interface, next hop IP. Most specific matching route, the matching route with the longest prefix. Is manually static. A value of an indicate value of 40100. Configure a static route specifying the next hop IP. IP route, IP address, and mask, and then next hop. Route with IHL of 0. What is the minimum value of IHL field? IHL field is 5. Configure a default route specifying the next hop IP. IP route 0.0.0.0 0.0.0.0 next hop IP. What does C in the routing table connected? What is the minimum length of the option field? Minimum length 0. To send a packet to a destination, does every network? No. A route is often used to direct traffic to the internet. Default route. Which field is used to identify which packet a fragment belongs to? Identification. The fragment offset field is 16 bits. 13. What is the Ethernet value of IPv4, IPv6? 86 DD. IHL field is blah 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 bits in length. IHL 4 bits. DTL time to live. Bit 0. 89 OSPF. Distributed. Oh. That's it. Code point. Differential surface. The SCP field is 8 bits, 6 bits. In Cisco IOS, what mode provides complete access to global configuration mode? Privileged exec mode. IPv4 header flags field bit df is done fragment, so bit 1 which is to indicate the position of fragment with fragment offset. Static routes in which you specify only the pair directly connected the interface, exit interface. ICMP is 1. Basically to define infinite TTL. Which two routes are automatically added to the routing table when you configure IP address local and connected? What maximum length of the IPv4 header? IPv4 header is 60 bytes. Prefix links do connected / connected. Depend on the network /24. Depend on the network. Yeah. Destination IP address is 32 bits. A computer network is digital telecommunication network which allow nodes for an host like PC to send packet outside of its network. It will send packet to its gateway, which will provide end-to-end notification of network congestion. ECN is a default route. MF is more fragment bit. Routers store routes to all of their known destination in the routing table. IPv4 packet, the fragmented is they're larger than the MTUs. Maximum option field length 40 bytes, MTU 1500, which field indicate the protocol of the encapsulated protocol. Show the routing table. Show IP route. In the routing table, the output gateway of last result is not set, means the default gateway is not configured. Recommended value of TTL is 64. Header protocol field value of 1 ICMP. The maximum value of total length 65535. Protocol field is 6 bits, 8 bits. Root and actual IP address on the interface local. The SCP field is 6 bits. What mode provide complete access to view device configuration. Privilege excite mode. The fragment offset field is fragment offset 8 bits. No, 13 bits. The SCP differentiated service code point. Protocol field is 8 bits. Okay, nice. Wait a moment, guys. I need to.
With the series. Also, please like and leave a comment, and share the video to help spread this free series of videos. Thanks for your help. This video, unlike the last one, is not going to be practical, meaning that you won't actually go on and configure a Cisco router or switch. Also, most of the information in this video won't be new. We've already covered most of it in previous videos. However, I decided to make this video because I think it's very important to make sure you have a good understanding of the complete process a packet goes through when being sent across networks. Hopefully, this video will be a little shorter than the usual ones. Let's get started. So, what will we cover in this video? We'll cover the entire process of sending a packet to a remote destination. This will include things like ARP, encapsulation, de-encapsulation, etc. Of course, there are different levels of depth we can go into when talking about this process, and I won't give unnecessary details that would only be expected of a CCNP or CCIE. But in this video, I hope to give you a solid understanding to get you ready for your CCNA. My hope is that this video will help you put all of the pieces together that we learned previously. So, this is the life of a packet, the process a packet goes through when being sent to remote networks. Here's the network topology we'll use for this video. If you watched Day 11's video, you should recognize this topology, as it's the same one we used to demonstrate static routing. We'll follow a packet being sent from PC1 in the 192.168.1.0/24 network to PC4 in the 192.168.4.0/24 network. Let's assume we have pre-configured static routes on these devices, so that the packet will follow the same path as in the static routing video. That is from PC1 to R1, R2, R4, and then PC4. This doesn't have to be the path the packet takes. The path that goes via R3 instead of R2 is valid too, but we'll stick to the same path as last time. Now, since we're not just looking at layer 3 in this video, let me add MAC addresses for these devices. I'll use 1111 for PC1. Now, as you know, a MAC address is actually 12 hexadecimal characters, but just to save space, I'll shorten them to 4. R1's G02 interface has a MAC address of AAAA, and its G00 interface has a MAC address of BBBB. That's something I didn't mention before. Each interface on a network device has a unique MAC address. Note that switch 1's interfaces also have MAC addresses. However, for this video, it's not necessary to know the MAC addresses of the switches, so to avoid clutter, I'll leave them out of this diagram. R2 has a MAC address of CCCC on its a MAC address of EEEE on its G01 interface, and FFFE on its G02 interface. I didn't make it all Fs because the MAC address of FFFF, 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 12 Fs, is the broadcast MAC address. So just to avoid confusion, I added that E on the end. One wants to send some data to PC4, one's IP address. Now because P2.168.4 address is in the 192.168.4.1, PC4's IP address. Now, because PC1's IP address is in the 192.168.1.0/24 network, it notices that the address 192.168.4.1 is in a different network. So it knows that it needs to send the packet to its default gateway, which is R1, something we have already pre-configured. However, in this example, PC1 has not sent any traffic yet, so it needs to use ARP, the address resolution protocol, something we covered in a previous video. Let's look at the ARP process once more. So, PC1 makes this ARP request packet. The source IP is its own IP address, and the destination is R1's G02 interface, which is the default gateway configured on PC1. Next is the MAC addresses. This is a minor point, but note that I put the source IP before the destination IP, but the destination MAC before the source MAC. That's because in the IPv4 header, the source IP address comes first, but in the Ethernet header, the destination MAC address comes first. Anyway, just a minor point. The destination MAC address is the broadcast MAC address of all Fs, because it doesn't know the MAC address of R1, so it will send the frame to all hosts on the network. Finally, the source MAC address is its own MAC address. So, it sends the frame, which switch 1 receives and broadcasts out of all its interfaces, except the one it received the frame on. In this example, only PC1 and R1 are connected to switch 1, so that means that switch 1 will forward the frame out of its G00 interface. To translate the meaning of this frame into English, that switch 1 will forward the frame out of its G00 interface. To translate the meaning of this frame into English, PC1 is basically saying, "Hi, 192.168.1.254, what's your MAC address?" Although I'm not going to really talk about the switches much in this video, note that switch 1 learns PC1's MAC address on its G01 interface when the frame arrives on its G01 interface. When this broadcast frame arrives in R1, it notices that the destination IP is its own IP, so it creates this ARP reply frame to send back to PC1. Although the ARP request message was broadcast, because R1 learned PC1's IP and MAC addresses from the ARP request message, the ARP reply can be sent unicast directly to PC1. So that's what R1 does. To translate this ARP reply message into English, basically it means, "Hi 192.168.1.1, this is 192.168.1.254. My MAC address is AAAA." Note that switch 1 will learn R1's MAC address from this message when the frame arrives on its G00 interface. So, now PC1 knows the MAC address of its default gateway, so it encapsulates the packet with this Ethernet header. Keep in mind, the original packet is not changed. The destination address remains PC4's IP address, not R1's IP address. Only at layer 2 is the destination set to R1's MAC address. So, it sends the frame to R1. R1 receives it and removes the Ethernet header. It looks up the destination in its routing table. The most specific match is this entry for the 192.168.4.0/24 network, which specifies a next hop of 192.168.12.2. So, R1 will have to encapsulate this packet with an Ethernet frame with the appropriate MAC address for 192.168.12.2. However, R1 doesn't know R2's MAC address yet, so how will it learn R2's MAC address? It will use ARP, of course. The source IP address of this ARP request will be R1's, and the destination will be R2's. The destination MAC address is all F's, the broadcast MAC address, because R1 doesn't know R2's MAC address, and the source is BBBB, which is the MAC address of R1's G00 interface. So, it sends the ARP request, and R2 receives it. Basically, what this ARP request says is, "Hi 192.168.12.2, what's your MAC address?" R2 receives the broadcast, and since the destination IP address matches its own IP address, it makes this ARP reply to send to R1. Once again, because it learned the IP and MAC addresses of R1 from the ARP request, it doesn't have to broadcast the frame. So it sends this ARP reply back, which basically says, "Hi 192.168.12.1, this is 192.168.12.2. My MAC address is CCCC." Okay, now R1 knows R2's MAC address, so it can encapsulate the packet with an Ethernet header, inserting R2's MAC address in the destination field. After receiving the frame, R2 removes the Ethernet header. R2 then looks up the destination IP address in its routing table, and the most specific match is this one for 192.168.194. Our destination ARP. R4 receives the broadcast. Once again, it sends 68. Address of moves the Ethernet is this entry for 192.168.4.0/24, which is directly connected via the G02 interface. But once again, R4 doesn't know PC4's MAC address yet, so you know what it has to do next. It will use ARP to learn PC4's MAC address. It prepares this ARP request frame. Again, the source IP and MAC addresses are its own. It sets the field of this since it is its IP and MAC network interface. My MAC address is 4444.254. This is 192.168.4.1. My MAC address is 4444. Note that switch 4 learns PC4's MAC address when it arrives on its G01 interface. Note that switch 4 learns PC4's MAC address when it arrives on its G01 interface. Now that R4 knows PC4's MAC address, it adds an Ethernet header to the packet, using its own MAC address on the G02 interface as the source address, and finally, it's always use of 192, the switch.4.1. Also, notice that the switches didn't actually modify the frames at any point. The switches forwarded the frames and learned the MAC addresses, but they don't actually de-encapsulate and then re-encapsulate the packet with a new Ethernet header routers so that the traffic follows and then reaching PC devices have always to device. So, that's it. Now, 1. PC4 sends a packet. Here is FPC1. Okay, let's source MAC address.
This is source MAC address when it is received on R1 G00 interface CCCP.
R2 it in question 3 when it is sent from
The source MAC address when it is sent from switch 1 G01 interface. Source MAC address
switch 1 floods it sends a packet to PC1.
The address when it is sent from R4 G01 interface 192.68.1.
The video to 3.168 addresses in range 2.16 PC1.
Source IP address when it is received on R1 192.68.168.41.
What is your answer? Which is the IP to its destination 168. There will be a packet that will be the next information. Anything else you want to vary? Today's video. Leave a comment and share the video. Video. Feel free to use or don't flash own new maybe the next practice. Okay, for this video there will once again be supplementary materials to help you practice it and test your knowledge. Feel free to make your own flash whatever you think is best if there is anything else you want to remember. You can also edit the flashcards I provide or delete some flashcards if you think some of them are not necessary. The flashcards are just a tool to help you, so feel free to use them however you think is best. Okay, that's all for today's video. Good luck with your studies.
PC1 pings PC4. Source is at PC1. Skip.
Welcome to Jeremy's IT Lab. This is a free, complete course for the CCNA. If you like these videos, please subscribe to follow along with the series. Also, please like and leave a comment, and share the video to help spread this free series of videos. Thanks for your help. Also, remember to download this Packet Tracer Practice Lab from the link in the description. It's coming of how in the network is in Mac Nation IP addresses will never change. The source will be PC1's IP address of 192.168.1.1, and the destination will be PC4's IP address of 100 and Mac, which just at Mac address. Not to actually IP conf address here, one where privilege G is 0-digit thing of my interface in the C. Check out that I, and it will use that one. That's what I did in this case to make it easier to remember. Let's check out that command to configure the MAC address. Show ifin address followed by the MAC address, and for node in the bottom, sent to let's from just node gigabit ether to our and let's check G0 here at word instance once decimal digit exact the gain for 3 through 4 as send it through and up to and the decimal. I'll simply C1 and now all are one Dutch. I'll click C1 your answer as for the MAC. Please subscribe to the tip. Check the links in the description. I'm also a welcome to Jeremy's IT Lab. This is a free complete course for the CCNA. If you like these videos, please subscribe to follow along with the series. Also, please like and leave a comment and share the video to help spread this free series of videos. Thanks for your help. In this video, we will be talking about subnetting. This is a very big topic for the CCNA, but not just for the test. It's an essential skill for a network engineer. Many people have trouble understanding subnetting, but let me assure you, it is not difficult. Subnetting is very simple if you take it step by step. So, I'm going to split subnetting into 2, or maybe even 3 videos, so we can take our time to really understand subnetting. There are already plenty of subnetting videos on YouTube. Of course, feel free to check out those videos too. There are some different tricks and techniques people teach that can speed up the subnetting process. I, however, will simply outline the basic steps involved in subnetting. I will avoid overcomplicating the topic. My end goal for these videos is that you understand and can do subnetting. So let's get started. So what will we cover in this video? Just a couple things. First is CIDR, pronounced CIDR, which stands for Classless Interdomain Routing. What exactly is that? Well, remember, I introduced the IPv4 address classes, such as class A, B, and C. Well, CIDR throws all that away and lets us be more flexible with our IPv4 networks. Then, of course, we'll cover the process of subnetting, taking it step by step so you don't get lost. Now, before I get into CIDR, let's review these IPv4 address classes, so we can then understand the need for classless IPv4 addressing. There are 5 classes of IPv4 addresses, A, B, C, D, and E. Class A addresses have a first octet beginning with 0, and the rest of the bits can either be 0 or 1. This leads to a decimal range for the first octet of 0 to 127. Remember, an IPv4 address is 32 bits, so there are 4 octets, 4 groups of 8 bits, in an IPv4 address. This makes the Class A address range from 0.0.0.0 through 127.255.255. Class A address range from 0 octets, 4 groups of 8 bits, in an IPv4 address. This makes the Class A address range from 0.0.0.0 through 127.255.255.255. Now remember, there are some special and reserved addresses in these ranges that can't be used for normal IP addresses on a device. But for this video, we'll just include all of them in Class A. Class B addresses have a first octet beginning at 110, and the others can be either 0 or 1. 192.0.0.0, 10. This means that the address is 255. As an IP address, as classes D and E have special purposes I mentioned in the IPv4 address length. Class last octet sticks to these classes. As you can see, there are few Class A networks available, only 128. Actually less than that because some are reserved, like the 127.0.0.0/8 range, which you may remember is used for loopback addresses. Because only the first octet of a Class A address is used for the network ID, there are 3 whole octets. Because only the first octet of a Class A address is used for the network ID, there are 3 whole octets available for addresses within each Class A network. So there are 16,777,216 addresses in each Class A network. That is 2 to the power of 24, because there are 3 octets, 3 times 8 equals 24 bits. Class B addresses are different. There are more Class B networks, 16,384, but 256 addresses per network, assigned to company authority. The I by a non-company get their own 2 networks, but only 256 addresses per network. So, how does a company get their own network address range to use? Well, IP addresses are assigned to companies or organizations by a non-profit American corporation called the IANA, the Internet Assigned Numbers Authority. The IANA assigns IPv4 addresses and networks to companies based on their size. For example, a very large company might receive a Class A or Class B network. Remember, there are lots of available addresses to use for hosts in each Class A and Class B network, while a small company might receive a Class C network, because there are fewer addresses in each Class C network, only 256. However, This system led to many wasted IP addresses, so multiple methods of improving this system have been created. Let me give you an example of how this strict system of addresses can waste IP addresses. So, here are two routers. As you can see, R1 has 3 networks connected to it here. Remember that routers are used to connect different networks, so each of these links are separate layer 3 networks, different IP networks. R2 also has 3 networks connected here. Perhaps each of these networks will have a few switches, with many end hosts such as PCs and servers connected to these switches. However, there is one more network here. That's this network connecting these two routers. This is known as a point-to-point network, meaning that it's a network connecting 2 points, in this case R1 and R2. For example, this might be a connection between offices in different cities, let's say San Francisco and New York. So, because this is a point-to-point network, we don't need a large address block, so let's use a Class C network, 203.0.113.0/24. Because this is a Class C network, there are 256 addresses in the network. -1 for the network address, 203.0.113.0, -1 for the broadcast address, 203.0.113.255, -1 for R1's address, which I'll assign as 203.0.113.1, and -1 for R2's address, which I'll assign as 203.0.113.2. That's a total of 4 addresses used, and 252 addresses wasted. Clearly, this is not an ideal system. Before introducing CIDR, here's another quick example of address waste. A company, Company X, needs IP addressing for 5,000 end hosts. This is a problem. Why? A Class C network does not provide enough addresses, so a Class B network must be assigned. Because a Class B network allows for about 65,000 addresses, this results in about 60,000 addresses being wasted. When the internet was first created, the creators did not predict that the internet would become as large as it is today. This resulted in wasted address space, like the examples I showed you, and there are many more examples that I could show you. The total IPv4 address space includes over 4 billion addresses, and that seemed like a huge number of addresses when IPv4 was created, but now, address space exhaustion is a big problem. There's not enough addresses. One way to solve or remedy this problem is CIDR. The IETF, Internet Engineering Task Force, introduced CIDR in 1993 to replace the classful addressing system. With CIDR, the requirements of Class A addresses must use a /8 network mask, Class B must use /16, and Class C must use /24 were removed. This allowed larger networks to be split into smaller networks, allowing greater efficiency. These smaller networks are called subnetworks, or subnets. Let's look at an example of splitting a larger network into a smaller network so you can see how it works. Here's the same point-to-point network we looked at before. Previously, it was assigned the 203.0.113.0/24 network space, but that resulted in lots of wasted addresses. Let's write this out in binary. Here's the binary, with the dotted decimal underneath. Now, the prefix length is /24, so here's the network mask, also known as the subnet mask, 255.255.255.0. Remember, all 1s in the subnet mask indicate that the same bit in the address is the network portion. In this case, I made the network portion blue, and the host portion is red. Well, how many host bits are there? 8, because it's 1 octet. So, how many potential hosts, or how many usable addresses are there? Well, the formula is this. 2 to the power of 8 minus 2 equals, in this case, so we have to remove them. 1 for R1 to be /24. Let's get some practice calculating the number of hosts within different prefix lengths. 203.0.113.0/. However, CIDR allows us to use different prefix lengths, so it doesn't have to be /24. Let's get some practice calculating the number of hosts within different prefix lengths. 203.0.113.0/25, 203.0.113.0/26, 203.0.113.0/27, /28, /29, /30, /31, and finally /32. I've put /31 and /32 in red because they're a little bit special. You'll see when you try to calculate it. So, pause the video here and try to calculate how many usable addresses are in each network.
-2.
Okay, let's check out the answers. So here is extended 255 part. Now there are 7 bits in the host portion of the address. Once again, how about in dotted decimal? Because 2 bits of the last octet are now part of the network portion. To use a /26 network mask for the 203 network, the masked bits as we expect 5.2 the network mask. This address host bits, there would be only 4 wasted addresses. In dotted decimal, there are 4 total addresses. That's the network address, before moving on to address, R1's address, and R2's address. That means 0 wasted addresses. Before moving on to look at the /31 and /32 prefix lengths, let me clarify a little bit. So instead of 203.0.113.0/24, we will use 203.0.113.0/30, which is a subnet of that larger class C network. 203.0.113.0/30 includes the address range of that larger class C network. 203.0.113.0/30 includes the address range of 203.0.113.0 through 203.0.113.3. Let me show you that in binary. Here is 203.0.113.0 in binary, the host portion all zeros. Here is 203.0.113.1, 203.0.113.2, and 203.0.113.3. These are the 4 addresses in the network. These 2 being the 2 usable addresses, which are assigned to R3.0.113.4 through 203.0.113.255, are now available to be used in other subnets. That's the magic of subnetting. Instead of using 203.0.113.0/24 and wasting 252 addresses, we can use /30 and waste no addresses. Or perhaps there is another way to make this even more efficient. Let's look into it. If we use a /31 prefix length, the mask is written as 255.255.255.254 in dotted decimal. There is now only 1 host bit, so that means 0 usable addresses. 2 to the power of 1 is 2, minus 2 for the network and broadcast addresses means 0 addresses that we can assign to devices. So you used to not be able to use /31 network prefixes because of this. However, for a point-to-point connection like this, it actually is possible to use a /31 mask. Let's check it out. So here's the 203.0.113.0/31 network. R1 is 203.0.113.0, and network, the only 2 addresses, .1. But for point-to-point networks like this, note that, but it is a configuration on a Cisco router, you'll get a warning like this, reminding you to make sure that this is a point-to-point link, but it is a totally valid configuration. So once again, the remaining addresses in the 203.0.113.0/24 address configuration. So 203.0.113.2 through 255 are now available to be used in other networks. But this time, we've saved even more addresses, using only 2 addresses instead of 4 for this point-to-point connection. People still do use /30 for point-to-point connections at times, but /31 masks are totally valid and more efficient than /30, so I recommend this method. But we still haven't looked at the /32 mask. A /32 mask is written as 255.255.255.255 in dotted decimal, making the entire address the network portion. There are no host bits. If you calculate this using our formula, you will get -1 usable addresses. Clearly, the formula doesn't work in this case. You won't be able to use a /32 mask in this case, and you will probably never use a /32 mask to configure an actual interface. However, there are some uses for a /32 mask. For example, when you want to create a static route not to a network, but to just one specific host, you can use a /32 mask to specify that exact host. Anyway, I'll talk about that later in the course. Just know that /32 masks are used at some points, but you don't have to worry about them for now.
In BigTime, you can collect BigTime cryptocurrency. It's real fun and easy. You can collect the BigTime token.
Here's a simple chart showing the dotted decimal subnet masks and their equivalent in CIDR notation. That's right, the way of writing a prefix with a slash, followed by the prefix length, like /25, /26, etc., is called CIDR notation, because it was introduced with the CIDR system. C network so far, 11s, dividing a larger network into smaller networks called subnets. Instead of using the whole 203.0.113.0/24 network for the point-to-point connection, we can use a /30 subnet and use only 4 addresses, or even better, use a /31 subnet and use only 2 addresses, and walk you through connected to R1, with many hosts connected to each switch in that 45 host number. You have received the 192.168.1.0/24 network, and you must divide the network into 4 subnets that can accommodate the number of hosts required. First off, are there enough addresses in the 192.168.1.0/24 network in the first place?
45. Yes.
So we need 45 hosts per network, including R1. But also remember that each network has a network and broadcast address, so that's +2. So we need 47 addresses per subnet. 47 times 4 equals 188. So there's no problem in terms of the number of hosts. 192.168.1. subnets to accommodate 4 is a Class C network. So there are 256 addresses. So we will be able to assign 4 subnets to accommodate all hosts, no problem. Okay, let's see how we can calculate the subnets we need to make. We need 4 equal-sized subnets with enough room for at least 45 hosts. Here, I've written out 192.168.1.0 with a /30 mask, 255.255.255.252. I skipped /32 and /31 since these aren't point-to-point links. We can't use /31, and definitely can't use /32. Since there are 2 host bits, The formula to determine the number of usable addresses is 2 to the power of 2 minus 2. 2 to the power of 2 is 2 times 2, which is 4. So that means there are 2 usable addresses in a /30 network. Clearly, not enough room to accommodate the 45 hosts we have. How bits? So the which is 8. But if we 2 addresses, bits, 2 times 2 times 2 times 2 to the power of, which equals 64. That means there are 62 usable addresses. So it looks like we found our number. /27 doesn't provide enough address space. /26 provides more than we need, but we have to go with 26. Unfortunately, you can't always make subnets have exactly the number of addresses you want. So, I think this video has gone on long enough. Instead of 192.168.1.0/26, what are the remaining subnets? To help you out, here's a hint. Find the broadcast address of subnet 1. The next address, after that, is the network address of subnet 2. Find the broadcast address.
To the power of 6, 63.
Address of subnet 1. The next address, after that, is the network address of subnet 2. And then just repeat the process for subnets 3 and 4. The rules so, post your answers in the comment section. We could be more flexibly clarify. However, also recently enabled views of the click professions. Thank you so much, you too.
不想花时间，好麻烦。宝丽镜口腔护具清洁定。
Welcome to Jeremy's IT Lab. This is a free, complete course for the CCNA. If you like these videos, please subscribe to follow along with the series. Also, please like and leave a comment, and share the video to help spread this free series of videos. Introduced why subnetting is necessary, and walked through a few examples. In this video, I'll try to give some more clear steps for solving subnetting problems. I've also decided to make one more video on subnetting, so this will be a 3-video series. So, what exactly will we cover in this video? We'll start with some subnetting practice questions, specifically for Class C networks, like last video. We'll start, of course, with the solution to last video's quiz question. After that, we'll look at subnetting Class B networks. The process is exactly the same, no matter what class of address you're subnetting, but it can be a little bit more difficult with larger networks. Class A networks will be covered in the next video, by the way. So, let's take a look at how to solve last video's question. I asked you to divide the 192.168.1.0, found that a /20 minute to... So, 92 the large the highest let's address 2.16 to 0 decimal. Net 2 means subnet binary to 120. The network address 192. Okay, we found the answer to the quiz. You may notice something about these numbers. 0 plus 64 equals 64. I said last video that I would just show you the basics of subnetting, not any special subnetting tricks, but let me show you just one that can help you figure things out faster. So, we found that a /20 octet, let me make it bigger. And the purple part is the bits from the right. Notice that the, let's see. Add 64 again, and we get 192.168.1.128, which is the network address of subnet 3, address of subnet 4. Add 64 again, and we get 192.8, the network address, which is the network address 92. Find the network addresses of each subnet. Now let's try another similar exercise. We have been given the 192.168.255.0/24 network, and have been asked to divide the network into 5 subnets of equal size. In this case, the number of hosts in each subnet hasn't been specified. So let's make 5 subnets that are as large as they can be.
plus 27.
So 0 bits .0 / borrowing 1 bit also means we can make 2 subnets received. If it's .168.2x, which is 2 to the and broadcast subtract borrowing 1 bit, so isn't enough. What if we borrow the number of borrowed bits? Well, we need 2 to the feed. We need just this video. Our first sub is the network, the last octet. What's the bit be able to count? /27, 27. Subnet 4.1 is 192.1 and we get 2. 3. 192.168.255.64/27. 192.168.255.128/20. However, it's R 192.168.255.160.192 and .224/27. Here's another type of subnetting question you might find. What subnet does host 192.168.5.57/27 belong to?
Two.
So we have the IP address of a host, 192. It's actually a... However, now to find 0, the subnet 192.168.5.32.29.219/29 belong to.
29 means 5. 5. 192 plus 32. 192. Plus 16. 208. You borrow 5, right? 5, then 1, 2, 4, 8. 16 plus 216.
Okay, let's network part N of the host 192.168.29 networks. Also, each subnet can contain 126 hosts. I recommend that you memorize these numbers. It will help you perform subnetting faster and easier than if you have to calculate everything every single time. Although these are fairly simple to calculate. For each, take note of split, the amount of hosts, except you have to doubles the number of subnets to calculate. For the number of subnets, each additional bit that you borrow doubles the number of subnets. For number of hosts, each host bit doubles the amount of hosts, except you have to subtract 2 for the network and broadcast addresses. Take note of /31. The number of hosts is 0. I mentioned this in the last video, but it's because there is only a single host bit, so there are only 2 possible addresses, which are taken by the network and broadcast address. However, for a point-to-point connection, you can actually use a /31 and assign those 2 addresses to each end of the connection, and have no network or broadcast addresses. Also, /32 technically uses all bits for the network address, allowing no hosts, but you can't assign a /32 mask to identify a specific host when writing routes and such, and in some other special cases. Now let's finally take a look at subnetting some larger networks, specifically Class B. Looking at this chart again, you can see that there are many more host bits, and therefore many more possible subnets that can be created with a Class B network than with a Class C network. However, the process of subnetting is exactly the same. So I'll just walk you through a couple examples with Class B networks, and then we'll leave Class A networks for the last video of this subnetting series. You have been given the 172.16.0.0/16 network. You are asked to create 80 subnets for your company's various LANs. What prefix length should you use?
80 subnets. So 2 to the power of 67/23.
Okay, this is really a simple question. This is the number of borrowed prefix length of /17. And if we write this subnet mask in dotted decimal, it is 255.255./7. That isn't /18. If we borrow another bit, net mask is 20 is 32 subnet. .255.252. Gives us 128 subnets. 128 subnets is more than we need, but /22 only allows for 64, which is not enough. I won't show you all 80 subnets, of course, but let's look at some of the subnets that can be made. The first being 172.16.0.0/23, of course. The next is 172.16.2.0/23. Notice I changed the last bit of the network portion to 1. Next is 172.16.4.0/23. You are required to divide the network into 500 separate subnets. What prefix length should you use?
500. 512. 512 is 64 is 6 plus 3, 9. So it's 25.
Pause the video and... Okay, let's go into 500 of the class 0.0/16. Here's another practice question. 25/26/27 at 72.18.0.0/16 network. Your company requires 250 subnets with the same number of hosts per subnet.
Fifty-six is 64 times 8.
Again, pause check out the next 8 bits allows us to make 250 hosts per subnet, this time with the class B network. What subnet does host 172.25.217.192/21 belong to?
Class 21. 127. 192. 0. 208. 208 plus 1. This one is 8, 4, 2, 1. And then slash 21. Then this will be 1, 2, 3, 4, 5. So only this. So 216. 216. That's 0.
0. And let's check the answer. Now part 72.1 test was exactly the same as for a Class C network. There are just more host bits, available host addresses for each prefix length when subnetting a Class B network. Don't worry, it's not necessary to memorize these numbers. That would simply be a waste of effort. Just know the patterns. For each host bit... Okay, let's go to question. Your company requires 100 subnets with at least 500 hosts per subnet. What prefix length should you use?
100 subnets. So 128. 128 is 2 to the power of 7. So slash 23. Plus 23, we still have 9. 2 to the power of 9 is equal to the power 8, 16, 2, 5, 12. Yep, that's enough.
Pause the video to find the answer.
Plus 23.
21.1/20. Okay, let's go to question 2. What subnet answer? What prefix length should you use? Pause the video to find the answer. Okay, let's go to question 2. What subnet does host 172.21.111.201/20 belong to?
Slash 20. 20 means power of 4. 111. 111 is 128. No. 64, yes. Oh, I just gone for addition. My method. 111 2 1. This one will be 55. 1 27. 1 13. 1 6 0 3 1 1. So it will be 110. 110 1110 slash 20. 20 means power of 4, so only this will be 1 2 4 8 16 32 96.
2 3 belongs to. What is the broadcast address of the network 192.168.9?
slash 26, it means it will borrow 2. Borrow 2. 192, 168, 91, borrow 2, so 0. Borrow 2, so it will still have 6, right? To the power of 6 equals to 64.
91.78/26 belongs to. Pause the video to find your answer. 16 network into 4 subnets of equal size.
Then network address of the second subnet 172.16.0.0/16. 4 subnets. 4 subnets, it means 2 borrowed bits. So it will become 172 16 dot finish progress then 18 plus 18, so we still have how many address, how many bits? 14 to the power of 14. No, it means 2 to the power of 6 and 2 to the power of 8. Zero dot zero slash 18 and 72.16.64.0/18. minus 255.
.0.0/16 network into subnet.
Subnets of 3 hosts each. How many subnets are you able to make? 1000 means we need 1024, right? 512, 512, 56, 56. This is 64 times 4, which means 26 minus 2, so 8 times 32. Really? Hosts. Oh, okay, it's my bad. And 04 24 equal to 12 times 2, 256 times 4, okay, times 2 times 2, 64 times 2, power of 4 to the power of 6 to the power of 4 to the power of 10. So we need 10 bits. Bit it means 22, right? 22, so 6 host bit, sorry, network bit, and then 10 host bit. How many subnet to the power of 6? How many is it? To the power of 6, 64.
Subnets of 1000, and then wait for the next video, where I'll go over the answers and explanations. Also, answers in the comment section of this video, and then wait for the next video, where I'll go over the answers and explanations. Also, there won't be any flashcards or practice lab for this video. After the next video, I will make a practice lab so you can subnet a network and assign IP addresses to the devices in each subnet, so wait for that. Before I wrap up this video, I want to give a shout out to my JCNP level channel members, Vance, Mike, Jonathan, and Lito. Thank you so much for your support. I really thank you for watching. That's all for this video. If you want to show your support, please subscribe.
有感冒症状就用普拿疼服冒加强定，30分钟快速有效缓解症状。
你有想过成为飞行员吗？你知道台湾其实一直都有免费的机会能够成为民航机师。
Welcome to Jeremy's IT Lab. This is a free, complete course for the CCNA. If you like these videos, please subscribe to follow along with the series. Also, please like and leave a comment, and share the video to help spread this free series of videos. Thanks for your help. This video will be the last of the subnetting series. Subnetting is very important to understand, so I wanted to take it slowly to make sure you don't get confused. In this video, we'll cover the last few important things you should know. So, what exactly will we cover in this video? First of all, I'll go over the answers to last video's quiz questions, called VLSM, which stands for Variable Class A Addresses. Then, we'll look at another topic in subnetting called VLSM, which stands for Variable Length Subnet Masks. I'll explain exactly what that is when we get to it. One from the last video. You have been given the 172.30.0.0/16 network. Your company requires 100 subnets, with at least we have borrowing 2 bits of bits 3 prefix length allows 510 usable addresses, 3. As I'm on to question 2. What subnet does host 172.21.111.201/20 belong to? These questions are easy if you remember the steps I taught you.
172.21.96.
Convert the address back to 201/20 and 3/26 belongs to. So to solve this problem, not the network address for the subnet. That's the broadcast address for this network. Let's check the answer for question 4 of equal size. Identify the network and broadcast addresses of the second subnet. So the first step is solving this. Have to borrow 18 prefix length. Change bits to 1. These are the answers to question 4. Finally, question 5. You divide the 172.30.0.0/16 network into subnets of 1000. We have to host. Allows for we can make 64 subnets. Look at meaning lots of room to rest. Okay, let's get to subnetting class A networks. Look at the size of rest bit field. That is the host portion. There are 24 host bits that we can borrow from, meaning lots of room to make subnets. However, let me remind you that the process of subnetting Class A, Class B, and Class C networks is exactly the same. So let's just do 2 practice questions subnetting Class A networks, and then let's move on to VLSM. You have been given the 10.0.0.0/8 network. You must create 2,000 subnets, which will be distributed to various enterprises. What prefix length must you use? How many host addresses or usable addresses will be in each subnet? Let's solve this question just like the other ones. Here is 10.0.0.0/8 in binary and dotted decimal. Solve this question just like the other ones. So only the first octet is the network portion, and we have 3 whole octets to borrow from and make subnets. Notice that I wrote the /8 subnet mask down here, 255.0.0.0. Currently we are borrowing 0 bits. Let's see it. Remember, 34, the /19 prefix length. Now how many hosts will be in each subnet? Well, there are 13 host bits remaining. So that means 8,190 hosts per subnet. So those are the answers. We will use a /19 prefix length, and there will be 8,190 host addresses, aka usable addresses, in each subnet. This is the same process we used for Class B and Class C networks. The numbers are just larger. 10.217.182.223/11. Identify the following for PC1.
Means network address 10.217, so it means 11 means plus 3, so it's like here. Wait. Standard broadcast address.
One subnet. Pause this. Here's the address writ 8. Change all of the host bits to 1, and you get the broadcast address, which is 10.19223.255.255. To determine the number of host addresses, 150 hosts per subnet is the same as for Class B and Class C network of the number of host 1 from the broadcast address, which is 10.192.0.1.255. Finally, 2 million the question. As to the larger numbers, its AB stands for Variable Length Subnet Masks. Until now, we have practiced subnetting using FLSM, Fixed Length Subnet Masks. This means that all of the subnets use the same prefix length. For example, subnetting a Class C network into 4 subnets using /26. However, VLSM, Variable Length Subnet Masks, is the process of creating subnets of different sizes to make your use of network addresses more efficient. Now, VLSM is more complicated than FLSM, but it's easy if you follow the steps correctly. So that's what I want to teach you now, the step to subnet a network using VLSM. So here's an example small enterprise network. There are 2 LANs in Tokyo and 2 LANs in Toronto. Tokyo LAN A has 110 hosts, and Tokyo LAN B has 8 hosts. Toronto LAN A has 29 hosts, and Toronto LAN B has 45 hosts. Also, there is a point-to-point connection between the 2 routers that we must assign IP addresses for. We are assigned the 192.168.1.0/24 network, and must divide it into 5 subnets to provide IP addresses for all hosts in the enterprise network. If we were to try this with fixed-length subnet masks, we would need to borrow 3 bits to make enough subnets. That would leave 5 host bits left. 5 host bits only allows 30 host addresses, so that's not enough addresses for Tokyo LAN A or Toronto LAN B. However, if we use VLSM, we can assign different subnet sizes to each LAN, which will allow us to make sure each LAN has enough addresses available. So what are the steps to subnet using VLSM? First, assign the largest subnet at the start of the address space. Then, assign the second largest after it, and then repeat the process until all subnets have been assigned, from largest to smallest. If you look at our network here, then repeat the process process until all subnets have been assigned, from largest to smallest. If you look at our network here, that means we will assign subnets in this order. First, Tokyo LAN A, which requires 110 hosts. Then, Toronto LAN B, then Toronto LAN A, Tokyo LAN B, and finally the point-to-point connection between the two routers. So let's do Tokyo LAN A. I want you to pause the video and figure out these 5 values by yourself. Network address, broadcast address,
You get 128, so 7 bits. 7 bits means we borrow 1. 25. Net address. Broadcast address. Broadcast first usable. Last usable. Usable host 2 to the power of 7 minus 2 minus 2 126. Is that correct? No, it's not. 2 to the power of 7. Oh, no, yeah, it's correct.
First, I know you can do. Let's check out the /25 pre addresses. Address is broadcast admin A. The first usable address is the network address 7 host bits. So we now have our first subnet, 192.168.1.0/25 for Tokyo LAN A. That /25 subnet uses up half of the address space of the 192.168.1.0/24 network, but that's no problem. Using VLSM, we can assign smaller subnets to these other LANs, and you'll see that there is enough address space left. So next, we should assign Toronto LAN B. So 192.168.1.127 is the broadcast address of Tokyo LAN A. If we add 1 to that, we will get the network address of the next subnet, which will be used for Toronto LAN B. Therefore, 192.168.1.128 is the network address of Toronto LAN B. But we're missing one important point. What prefix length should we use for Toronto LAN B? So with this information, I want you to do the same thing for Toronto LAN B.
Toronto LAN B. 45 hosts means 64, 6. So it will be 26.
Pause the total number of. Let's check. That leaves 6 hosts with a /20s, 1 to broadcast at. 192.128 hosts. That needs 6 prefix. Okay, let's check the answer.
And 28, 2 tens to the power of
which allows prefix length 2.1 address 192.168.1 and Toronto LAN B, we've used address space from 192.168.1.0 through 191. For more smaller these two subnets take up 3/4 of the address space, but that's no problem. There is still room for more smaller subnets. 192.168.1.191 is the broadcast address of Toronto LAN B. So 192.168.1.192 is the network address of Toronto LAN A. Once again though, we have to figure out what prefix length to use for Toronto LAN A.
So 32. 32 means to the power of 5. 5. 27. And 92 plus 765 32. 2, 2, 3. First usable.
Let's do the same process as with the other LANs. Hopefully you found the answers, prefix length 192/27. With this information, let's check out Tokyo LAN B next. So we've used all the way to 192.168.1.223.
Host bits. 8 hosts, so we need 16. 16 is 4. 428.
Is Tokyo LAN B's network. Please pause. Okay, 8 prefix length. One possible remember or Tokyo LAN is for Tokyo LAN and B, these two routers. So we've used address space all the way up to 192.168.1.239. There's not a lot of space left, but that's no problem. Point-to-point connections only require 2 addresses. 192.168.1.239 is the network address of Tokyo LAN B. Therefore, 192.168.1.240 is the network address of the point-to-point connection. Now, what prefix length should we use? So, as I mentioned in the first subnetting video, it is possible to use a /31 prefix length for a subnet requiring only 2 hosts. However, for the CCNA test, if you are asked what prefix length to use for a subnet that requires 2 hosts, I recommend not using a /31. Instead, what other prefix length allows for 2 hosts? Pause the video here and find your answers.
And then 2, 4.
.192 test address. One for the Tokyo router and one for the Toronto router. Okay, so we successfully subnetted this different prefix length. SM, we start with the largest repeat until you continue practicing subnetting using OM, subnetting.org, here, and sample question from subnettingquestions.com. It's similar to the ones we have been doing in these videos. And here's those other two websites. Subnet is question from each of those practice websites every day for at least 1 week. At least one practice question from each of those practice websites every day for at least 1 week. Here is some homework. There's lots of other from questions.com. Check them out and try out questions from each subnetting.org.
The first valid host address on the fourth subnet. What address? 27 means we have 5 bits, right? Bits is then 32, so 32 times 0, 32, 64, 96, so 96.1. No, it's not like that. 97. Yep. What is the first valid host address for is a part of? Valid host address on the subnet. Is a part of OK19, so it will be 19 means 16 plus 3, 16 plus 3, so it's just 0, 0. So 0, 1.
And subnettingpractice.com. Check them out and try out questions from each site. Here's an example question from subnettingquestions.com.
音乐支付，音乐支付，全支付。
A direct connection between two routers is called a point-to-point network. Classless inter-domain routing. Classless idea. User for smaller network are called subnet. What is the formula to determine the number of usable address in a network? 2 to the power of n minus 2. What is the definition of /25 prefix length? 255, 255, 255, 128. 255, 255, 255, 192. 255, 255, 255, 224. 255, 255, 255, 240. 255, 255, 255, 248. 255, 255, 255, 252. 255, 255, 255, 254. 255, 255, 255. 128 slash 25, 26, 27, 28, 29, 30, 31, 32. Point-to-point connection network. 26, 192. Subnets. Classless interdomain routing. CIDR to 128 is equal to the power of n minus 2. 3 means 2 to 4. Okay, 240 192 plus 32 29 no 28 240 27 per so plus 3 92 plus 54 31 is 254 224 is 27 30 252 slash 25 248 means 192 224 240 248 5, so it means 29. This one will be 31 255 29 is 4 240 248 and the third and 226 29 oh that's my mistake, should be 5 248 252 means 30 32 28 4 240 248 okay.
Welcome to Jeremy's IT Lab.
Sufficient guessing for each land. Hosts means 2 to the power of 7 minus 2. 7 hosts bit 7 128 126 hosts, so because 7 hosts bit make it 2.168.5.0/25. And then the broadcast address would be 127.25 first usable address after 1/25 for last usable address 126/25. Now it will be in the 45. 45 means it's the next one is next to 68.5.128 slash, because it's in 45, then closest one is 64. 64 to the power of 6 minus 2. Power of 6 means 26. So the broadcast address will be 26, 64, 63, 191 to 168.5.129, 192.168.5.190 plus 26. Next one, how many hosts? 14 hosts. 192, 168.5.192 slash, because we only need 14 hosts, then we can use 16. 16 means how many? It's 16 to the power of 4. 28. For page 15, 207. The 2.168.5.193. 28. So we will have 7 plus 6, yeah, exactly 192 168.5.208 slash same 28. Two plus 12, 14. Next, the last one. Assign the first user PC in each LAN. Default gateway. I will go to this first. No, it's a mistake. No, it's not. G00 IP address. G00 90 126 225. Okay, right. Then go to the router 2. And then we go to G00.
This is also remember to subnet video. This is about one largest subnet at the start of the address in the with the land low addresses for 60 and both. As one, first, let's assign the addresses to PC2 and R192.168.5.127, both /25. R1 below it, and for so let's enable the interface with no shutdown. Let's confirm our configuration. Do show IP interface G01. The show IP interface command shows various information about the interface, primarily layer 3 information. You can see here that the IP address has been configured correctly. You may notice the broadcast address of 255.255.255.255. This address basically functions the same as the subnet broadcast address of 192.168.5.127, and it can be used for any network. When we configure other IP addresses and use this show IP interface command, those other interfaces will display the same broadcast address too. Keep in mind, if a host sends a broadcast to 255.255.255.255, it won't be sent to all networks. It will still stay in the local subnet, and a router will not route it to other networks. The subnet broadcast address, however, 192.168.5.127 in this case, can be used by hosts in other subnets to send a broadcast to this subnet. Anyway, I think I'll explain that in a lecture video in the future, so don't worry about it. I just wanted to explain it since you can see it here. Okay, now let's configure PC2. Click on 26. Is to fill in the subnet mask 8 document and requires to look at LAN 1. And a slash address, so it's 192.1 is 1 first, 00255 no 2 the 13 whom next. All of the routes work. 1C9. Talking, you should see that PC1 can now read as the 1 2 then exit LAN 2 for our go back address okay, that's it 255 connected and locally 3 first 5.240. Then the next hop of 192.5. Okay, look D4 to make sure our routes work. Really, you should try to ping all other PCs, but I'll show just one. Okay, so from PC1's 09, let's ping to PC4. It hasn't completed yet. There may be a few failures, but if I keep talking, you should see that PC1 can now reach PC4. Okay, so we have successfully subnetted and configured a network, and then configured static routes to provide reachability. That's all for this lab. Thank you for watching. Please subscribe to the channel, like the video, leave a comment, and share the video with anyone else studying for the CCNA. If you want to leave a tip, check the links in the description. I'm also a Brave verified publisher and accept BAT or Basic Attention Token tips via the Brave browser. Welcome to Jeremy's IT Lab. This is a free, complete course for the CCNA. If you like these videos, please subscribe to follow along with the series. Also, please like and leave a comment, and share the video to help spread this free series of videos. Thanks for your help. So, today's topic is another big one. Today's topic is VLANs. VLAN stands for Virtual LAN, Virtual Local Area Network. It's very important that you understand VLANs well for your CCNA exam, and certainly when working as a network engineer. So, feel free to ask any questions if you don't understand. Here are the topics we will cover in today's video. First, what is a LAN? We know it stands for Local Area Network, but I'll give you a more specific definition. To help understand LANs and VLANs, we will also look at broadcast domains. After looking at LANs and broadcast domains, I will introduce you to VLANs, virtual LANs. I will teach you the basics of VLANs and their purpose. Finally, we will look at the basics of VLAN configuration on Cisco switches. By the way, this won't be the only video on VLANs. The next video, day 17, will also be on VLANs, so this video will just cover the basics. Let's get started. So, what is a LAN? In a previous video, I said that a LAN is a group of devices, PCs, servers, routers, switches, etc., in a single location, for example, a home or office. Let's take a look at a more specific definition. A LAN is a single broadcast domain. A broadcast domain is the group of devices which will receive a broadcast frame, that is, a frame with a destination MAC of all Fs, sent by any one of the members. Let's take a look at a diagram. So, take a look at this network here. How many broadcast domains do you think there are?
3.
Remember, a broadcast domain includes all devices that will receive a broadcast frame. So, let's say PC1 sends a broadcast frame. And remember that a broadcast frame is a frame with a destination MAC address of all Fs. Which devices will receive the frame? Well, this PC1 sends a frame out towards switch 1. And what does a switch do with a broadcast and R1? What does a router do with a broadcast frame? It doesn't forward it. It will receive the frame, but it won't send it to other networks. So that means this is one broadcast domain, including PC1, PC2, switch 1, and one of R1's interfaces. So that's one broadcast domain. How many are left? What if PC3 sends a broadcast frame? Which devices will receive it? Switch 2 will receive the frame and flood it out of all interfaces to R1, PC4, and PC5, D4 domains, and switch 3. So we found 3 broadcast domains so far. However, there is one more. What if R1 sends a broadcast frame out of its interface which is connected to R2? It will be received only by R2. However, even though this is a connection between only two devices, it is still technically a broadcast domain. So, do you understand what a broadcast domain is now? A broadcast domain is the group of devices which will receive a broadcast frame with a destination MAC address of all Fs sent by any one of the members. In this network here, there are 4 broadcast domains, and therefore 4 LANs. Here is a small LAN of a company. Let's say there are 3 main departments in this office: engineering, sales, and human resources. Also, the company is using the 192.168.1.0/24 network for this LAN. However, this isn't necessarily the best setup. For both security and performance purposes, it will be best to split up these into separate subnets. For example, let's say security 1 engineering. Here is a small LAN of a company. Let's say there are 3 main departments in this office: engineering, sales, and human resources. Also, the company is using the 192.168.1.0/24 network for this LAN. However, this isn't necessarily the best setup. For both security and performance purposes, it will be best to split up these into separate subnets. For example, let's say a PC in the engineering department sends a broadcast message intended for other PCs in the engineering department. Since it's a broadcast message, the switch will flood it out of all interfaces. So, not only will the PCs in the engineering department receive the broadcast, all PCs, as well as the router, will receive the broadcast. This is a problem for both security and network performance purposes. When it comes to performance, lots of unnecessary broadcast traffic can reduce network performance. Whether it's a broadcast from one end host, or a switch that doesn't know how to reach the destination MAC address so it floods the frame, we should minimize unnecessary traffic in our network. As for security, even within the same office, you want to limit who has access to what. You can apply security policies on a router or firewall. Because this is one LAN, PCs can reach each other directly, without traffic passing through the router. So even if you configure security policies on the router, they won't have any effect. We should separate these hosts so we can apply security policies that determine who can access what in the network. So let's split up these departments into separate subnets: 192.168.1.0/26 for the engineering department, 192.168.1.64/26 for the HR department, and 192.168.1.128/26 for the sales department. However, there's one problem. The router is going to need an IP address in each subnet, so it will need one interface in each subnet. So let's replace this single connection between the switch and router with 3 separate connections, one in each subnet. Actually, there is a more efficient way of doing this. You don't actually have to use 3 separate interfaces, but don't worry about that for now. I will cover that in a future video. So, you may think the problem is solved now. Let's say this PC in the engineering department has an IP address of 192.168.1.1, and this one sends some data to PC2. PC1 will recognize that PC2 is in a different subnet than its own, so it will set the destination MAC address to its default gateway, R1. This is what the frame will look like: source IP of PC1, destination IP of PC2, source MAC of PC1, and destination MAC of R1. PC1 will forward the frame to the switch, which will send it to R1, which will then change the source MAC to its own MAC, and the destination MAC to PC2's MAC. It will then forward the frame back to the switch, which will then forward it to the destination, PC2. Okay, so instead of PC1 being able to send traffic directly to PC2, we forced it to send the traffic through R1 first, where we would have configured some security policies and such to control exactly what traffic is allowed to pass between these subnets. However, there is still a problem. Here's the problem. What if the frame is a broadcast or unknown unicast frame? The switch will flood the frame out of all interfaces. For example, here's a broadcast frame. The source IP is PC1's IP, and the destination IP is its subnet's broadcast address. So, this is a broadcast frame intended to the engineering department. The source MAC is PC1's, and the destination is the broadcast MAC address of all Fs. Where is the problem? Well, remember that a switch is only aware up to layer 2. It looks at layer 2 information like source and destination MAC addresses only. It doesn't care about layer 3, 4, etc. So, even though there are 3 separate subnets here, the switch doesn't know that. PC1 will send the frame to the switch, it will see the destination MAC address of all Fs, and then flood the frame. I'll say it again. This is bad in terms of both network performance and security. So I've shown you that, although we separated the 3 departments into 3 subnets, meaning they are separated at layer 3, they are still in the same broadcast domain, the same layer 2 network, or the same LAN. Now, one possible solution is to buy a separate switch for each department. However, that is not very flexible, and network equipment isn't cheap, so buying 1 or more switches for every single department could be too expensive, especially for a small enterprise. However, this is where VLANs come in. Although these PCs are all in the same LAN, local area network, we can use VLANs, or virtual local area networks, to separate them at layer 2.
Want to get into software development, data analytics, or IT and security? Well, do yourself a favor.
We'll assign the engineering department to VLAN 10, the HR department to VLAN 20, and the sales department to VLAN 30. How exactly do we assign these hosts to VLANs? We configure them on the switch. More specifically, on the switch interfaces. You configure the switch interface to be in a specific VLAN, and then the end host connected to that interface is part of that VLAN. The switch will consider each VLAN as a separate LAN and will not forward traffic between VLANs, including broadcast or unknown unicast traffic. So, if we have set up these VLANs, if PC1 sends this broadcast frame, after the frame arrives at the switch, it will be forwarded to all interfaces in the same VLAN. Because the broadcast arrived on an interface configured in VLAN 10, the switch will only forward the frame to other interfaces in VLAN 10. If PC1 wants to send the same unicast frame to PC2, it will function just like before. It sends it to the switch, which sends it to the router, which changes the source and destination MAC addresses, and sends it back to the switch, which sends it to the destination. Notice that the router is used to route between VLANs. The switch does not perform this inter-VLAN routing. It must send the traffic through the router. Notice that traffic arrives on a VLAN 10 interface and is forwarded out of a VLAN 10 interface. Also, traffic that arrives on the VLAN 30 interface is forwarded out of a VLAN 30 interface, both in the same VLAN. A switch will never forward traffic directly between two forwarded out of a VLAN 30 interface, both in the same VLAN. A switch will never forward traffic directly between two VLANs like this. Well, first of all, the two hosts are in separate subnets, so PC1 itself will send the traffic to its default gateway, R1. However, even if PC1 and PC2 were in the same subnet, the switch wouldn't forward the traffic from PC1 to PC2, because they are in separate VLANs. Just a bit of review. VLANs are configured on switches on a per-interface basis. We're physically connected to the same switch, and therefore in the same broadcast domain, traffic directly between hosts in different VLANs. As I showed you, the switch must forward the traffic to a router. Actually, there are a couple other methods of inter-VLAN routing, and I will cover them in a future video. Finally, let's take a look at basic VLAN configuration. I've added the interface numbers to the diagram. Interfaces in VLAN 10 are G10 through G13. Interfaces in VLAN 20 are G20 through G22. And interfaces in VLAN 30 are G30 through G33. Let's go into the CLI and put these interfaces into the proper VLANs. Before configuration, let's look at the VLANs that exist by default on a switch. In this output, you can see I use the command show VLAN brief. It displays the VLANs that exist on the switch and which interfaces are in each VLAN. Here you can see VLAN 1 with the name default. This is the VLAN that all interfaces are assigned to by default. So even if you don't configure any VLANs, all interfaces are in VLAN 1 by default. Under ports, you can see all of the interfaces on this device, from G00 to G33. Under it are 4 other VLANs, 1002 to 1005, used for FDDI and token ring. These are old technologies that you don't need to know for the CCNA, but feel free to Google them if you're curious. VLANs 1 and 1000 to 1005 exist by default and cannot be deleted. Remember that. This is how you assign interfaces to a VLAN. First, I use the interface range command to configure all of the VLAN 10 interfaces at once. Use the switchport mode access command to set the interface as an access port. What is an access port? An access port is a switch port which belongs to a single VLAN and usually connects to end hosts like PCs. That's why it's called an access port. It gives the end hosts access to the network. There is another important type of switch port called a trunk port. Switch ports which carry multiple VLANs are called trunk ports. I will cover trunk ports in depth in the next video, but for today's video, we will focus only on access ports and take it step by step. A switch port connected to an end host should enter access mode by default. However, it's always a good idea to explicitly configure the setting and not rely on auto-negotiation of port type. Anyway, the last command after configure a switch port connected to an end host should enter access mode by default. However, it's always a good idea to explicitly configure the setting and not rely on auto-negotiation of port type. Anyway, the last command after switchport mode access is switchport access VLAN 10. This is the command that actually assigns the VLAN to the port. Notice the message that appears after this command. Access VLAN does not exist. Creating VLAN 10. Because VLAN 10 didn't exist on the device yet, it was created automatically when we assigned the interface to VLAN 10. I'll show you how to manually create a VLAN in the next slide. Next, I again use the interface range command to configure all of the VLAN 20 interfaces at once. I use the same switchport mode access command, then switchport access VLAN 20 to assign the interfaces to VLAN 20. Finally, I did the same for VLAN brief command once again. And here you can see the 3 VLANs we created, and the ports we assigned to each VLAN. Notice the default names of each VLAN. Let's change those to make it more understandable. So, I use the VLAN 10 command to enter configuration mode for VLAN 10. By the way, this is the command to create a VLAN also, but in this case, it was already automatically created when we assigned the interfaces. Next, I assign the name with this simple command, name engineering. Then I do the same for VLAN more with show VLAN brief. Notice that the names have been changed to engineering, HR, and sales. Okay, so that's all for the configurations. If I use the command ping 255.255.255.255 on PC1, which sends a ping with the destination MAC address of all Fs, the broadcast MAC address, the broadcast will only reach hosts in VLAN 10. Likewise, if I use the same command on PC2, the broadcast will only reach PCs in VLAN 30. Okay, so before moving on to today's quiz, let's review what we covered. We talked about what a LAN is, and I defined it as a broadcast domain, the group of devices that will receive a broadcast frame sent by another member in the group. Then I talked about what a VLAN is. It's essentially a way to logically split up a layer 2 broadcast domain, to make multiple separate broadcast domains. We also talked about the purpose of VLANs. The two big reasons are network performance and security. VLANs help to reduce unnecessary broadcast traffic, which helps prevent network congestion, and therefore improve network performance. Limiting broadcast and unknown unicast traffic like this also improves network security, since these messages won't be received by devices outside of the VLAN. You should always make sure that network traffic isn't sent unnecessarily to other devices, as much as possible. Finally, we looked at how to configure VLANs on Cisco switches. Specifically, we configured access. Let's go on program. Pause the video and count how many broadcast domains you see.
1, 2, 3, 4, 5, 6, 7.
Pause the video and let's check question 2. How many broadcast domains are shown in this network diagram?
1, 2, 3, 4, 5.
And the connection between the two routers is a broadcast domain as well. That doesn't exist. A, the command will fail. Or D, all VLANs exist by default. Pause the video to think of the switch will yet. 3 sends a broadcast message. How many devices will receive it?
PC3. 2.
D. So the router and the other PC in VLAN 20, making a total of 3 devices, of all interfaces in VLAN 20. So the router, and first of all, the switch will receive it, then it will send it out of all interfaces in VLAN. No VLANs will receive it, 20 and 30 on a Cisco switch. How many VLANs will be displayed in the output of the show VLAN brief command?
5, 6, 7, 8, 9.
A. 3 out your answer.
8.
Total VLANs. VLANs 1 and 1002, 3, 4, and 5 exist by default. You've learned. Jonathan, sorry if I pronounce. If you want to leave a tip, check the links in the description. I'm also a Brave verified publisher and accept BAT or basic attention token tips via the Brave browser.
Trunk port. 1. VLAN 1. Switch port mode access. Switch access port. Broadcast domain at layer 2. Create a VLAN. Create a VLAN. VLAN name or number. Name VLAN name. Broadcast domain. Switch interface to be an access port. Switch port mode access. Forward traffic. No, it will not. VLAN 1, 1002, 1003, 4, and 5. And belong to a single VLAN is connected to n host an access port. Configuration of a switch access port. Switch port, VLAN number. Access VLAN. VLAN are used to split up broadcast domain. Configure the VLAN of a switch access port. Switch port, access, VLAN number. What VLAN RTCO interface VLAN 1. Configure a switch interface to be an access port. Switch port mode access. Create a VLAN. Create a VLAN switch. VLAN ID or number. Okay, multiple VLANs are trunk port. What are the 5 VLANs that exist by default on a Cisco switch? VLAN 1, 1002, 1003, 1004, 1005. Configure the name of a VLAN. Name, VLAN name. A broadcast domain. VLAN operate at layer 2. Will a layer 2? No. Port is to single and usually connect to end host. Access. Configure VLAN of a switch access port. The VLAN of a switch access port. Switch port. What is the VLAN? Switch port access. Switch port access. VLAN number. Oke, thank you guys. Kita istirahat dulu ya. Bye bye.